Ever notice how water sticks to the back of a spoon? Air does something just like that, and it's part of what keeps planes flying. Today, we're discussing yet another way that wings generate lift. The airflow hugs to the top of the wing, changing its velocity from horizontal to angled down. The downward force on the air causes an upward reaction force on the wing. Before I get carried away, let's quickly review some vocabulary. This shape is called an airfoil and is the cross-section of an airplane wing. The leading edge is the forward part of the wing. The trailing edge is the back of the wing, and the chord line is a straight line connecting those 2 points. The Coanda effect is the tendency of fluids to stick to surfaces they encounter. A boundary layer is a thin region of fluid near a surface where viscous forces dominate. We'll go into more detail on all of these concepts, so don't worry. Going back to my original claim, you might ask why the air molecules follow the shape of the wing, rather than hitting the top and continuing on their path in a straight line. It's because of the Coanda effect. All real fluids have some amount of viscosity. The word sounds fancy, but it's just a fluid's internal stickiness. How much it resists sliding past itself. Honey? Super viscous. Water? Low viscosity. Air? Even lower, but it's not zero. And because it's not zero, air molecules stick just a little to the surfaces they touch. So air molecules are affected by the presence and shape of an airfoil. When air flows over a wing, that slight stickiness means the first thin layer of air molecules cling to the wing's surface. Thanks to the Coanda effect, the moving air is dragged along the wing's surface, and instead of shooting straight ahead, it follows the curve of the wing's top. We explored the camber of a wing in a previous video, but it's important to know that the top of the wing is curved, rather than flat like the bottom. Looking at this representation of an airfoil, it's also good to note that the leading edge is thick, and the trailing edge comes to a thin point. So for the air molecules flowing over the top of the wing, we can see that they would have to bend downward as they travel to the trailing edge. If you change the direction of something's motion, you're changing its velocity. This means a force is present. The wing bends the airflow downward, but here's what that really means. Due to the air's viscosity and the Coanda effect, the air is pulled down by the wing. As the air experiences a downward force, the wing experiences an upward force. Newton's third law supports this. As the air is pushed down, it is pulling up on the wing, generating lift. It's the same reaction force you feel if you stick your hand out a car window and tilt the front of your hand slightly up. The air gets shoved down as it clings to the back of your hand. As a result, your hand gets shoved up. Now, about that clingy layer of air molecules. We call it the boundary layer. It's super thin, but it's where all the action happens. Right at the wing's surface, the air speed is literally zero because of high viscosity. The air particles, just a molecule wide, on the top of the wing have the strongest attraction to the surface of the wing. Each layer of particles above has more and more velocity since they are pulled downward less. The air speeds up until it's moving with the free stream. That velocity gradient is the boundary layer. If the boundary layer stays smooth and attached, the Coanda effect works beautifully. The air follows the wing's curve. Lift is strong, and everyone's happy. But if the boundary layer separates, the airflow stops hugging the wing, lift drops, and suddenly you're talking about stalls. This can occur for several reasons, one of which is if the angle of attack is too great. If the front of the wing is angled upward too much, the air's molecular attraction won't be strong enough to adhere it to the surface of the wing, so the airflow will separate from the airfoil. Without the downward force that was previously produced by the boundary layer, the resulting upward force is weakened, meaning lift is lost. So, velocity lets air stick. The Coanda effect makes it follow the wing's shape, and the boundary layer makes that connection stay strong. Together, they explain why a wing can bend air down and get pushed up in return. Next time you watch a plane take off, just imagine millions of teeny air molecules playing follow the leader along the wing. all thanks to a little stickiness.